Okay, so we continue with our exploration of the complex analysis. So let's see. So today we study what we maybe briefly started the last time. We start with the Cauchy integral formula, which is to say now here C is a closed contour in the complex plane that contains the point z0 and that is traversed in the counterclockwise. So I just label it as this, in the counterclockwise direction. And of course, we assume that the function f is analytic at all points yeah, so that is it. So how do we start this? In the region. Okay, so we begin by typically drawing sky, and what I'll do is that so let's say I had this particular contour, I had this z0, and that was the idea. So this was in the counterclockwise, so this counterclockwise loop. So let me try to redraw this. So I have this guy, imaginary z, real part of z, and so this was my z0. Why don't I just So in this contour, I'll just redraw this by imagine this contour. So I'll call this circle as C1. These points are, let's say, A, B, and I am imagining this particular contour which is going in this direction. It traverses C in this direction, comes here, goes through the circle in the clockwise direction, and then again returns over there. And I'm going to make these points shrink. So this is, let's say this was uh, path 1, this was path 2. So P1 and P2, I'll shrink them so that they are overlapping. So what do I have then? I have my contour C, which was my original integral, and I need to evaluate this guy. Now, if you notice that what do I have? I have my new path, which was, let me call it, this whole entire path was, let's say, some C0. So I have C0 was nothing but C, which was the original contour, which was this guy, plus this mini circle C1. So I'll have this guy C plus C1, because as I shrink these points P1 and P2 over here, my C0 is nothing but a combination of this path plus this circle. And as P1 and P2 are equal and opposite, they'll cancel each other. So I have this guy C0, my new path, which was traversing this. I'll just maybe use a different pen. Yeah, so this was my C0, this particular path, this guy, this guy, this guy, this guy. So I have this guy C0 as C1, C plus C1. C was my original contour, and as I shrink P1 and P2, this is equals to C plus a mini circle over here, C1. So writing in terms of the integral, so that's the idea, and this was my point Z0. So as Z goes to Z0, we also notice that the radius of the mini circle shrinks. So I have 1 over 2 pi iota Fz over Z minus Z0 dz is equals to 1 over 2 pi iota C. So this integral over C0 path is nothing but breaking into two integrals. One, the original thing we wanted C, plus integral over C1, which was my mini circle. And Notice I am going to label it clockwise because this was in the clockwise direction. This path is clockwise path. Okay, so what do I have? Notice that this guy goes to 0. Since this particular path, actually, if you notice, this has excluded this point. So this was the contour, this was the area. So this path, C0 path, which starts from over here, this path has actually excluded this point. So if my contour does not involve the point, then my integral I've already seen is 0, because we've already assumed that from the Cauchy's theorem, and we already know Fz is analytic in the region where I'm specifying my contours. So I'm left with this guy. So this guy, what does it mean? This means 1 over 2 pi iota integral Fz over z minus z0 dz is nothing but minus 2 pi iota integral c1 clockwise direction Fz z minus z0 dz, and of course the limit over here is limit z is going 0. The circle is shrinking very narrowly, and these guys are p1 and p2 are shrinking very narrowly. So putting this clockwise, anti-clockwise, I'll change the integral sign. So what do I get? I get this as, this guy is, consider the RHS, which is 1 over 2 pi iota to 0. I have this guy. Now what I'll do is that I need to evaluate this integral, and then I'll get the integral I needed for the Cauchy's integral formula. This was my original contour over here. So for this, I put z minus z0 as sum in its polar form, and then the differential element is nothing but uh, the derivative of this guy. Notice as z goes to 0, 0, r goes to 0. As this point approaches, as my contour path, I'll have to redraw it again probably. As my contour path approaches the point z0, the radius goes to 0, and the circle becomes smaller and smaller. Circle becomes smaller and smaller, but with a constant radius. So that's my differential element. I still will have to traverse the whole 0 to 2 pi to integrate it. So what do I get? I get the RHS as plus 2 iota, 2 pi iota, contour integral now anti-clockwise because I have changed the sign. Minus was clockwise and I have put plus as anti-clockwise, and that's going to be Re iota theta. I'm just plugging the value of z. So z is nothing but, if this guy is given, then I have z as z0 plus Re iota theta. That's what I plugged in here. I plug in the value of dz, which was nothing but r iota e iota theta d theta, and in the denominator I have z minus z0, which was r e iota theta. So I cancel the terms. What do I get? I get as r goes to 0, I'll take the limit. So I'll just cancel these guys. I take the limit. So that just becomes a constant which comes out of the integral fc0 over 2 pi iota, and I am left with an integral over basically theta. So I have iota also comes out of the integral over here. I have the integral over the theta which gives me 2 pi. So I have nothing but I get fc0 2 pi iota divided by 2 pi iota, which gives me fc0. Okay. Okay. So that was what was required to be proved. So I have the uh, Cauchy's integral theorem. I'll just rewrite again. Let's rewrite the Cauchy's integral formula again, which was nothing but the function's value evaluated at c0 is nothing but the value of this integral dz. Okay, so what can I do more about it? So let me just express this as some fk. I'm just changing the variable over here, and I'll keep z as the variable of my integration, z minus k dz. Now what I can do, I can take a derivative. So that gives me fc over z minus k the whole square dz. I can take the double derivative. That gives me fc, and 2 will come out. I'll get k whole cube dz, so on and so forth. So generalizing this, what do I get? I get the nth derivative f and k, which was nothing but taking the derivative of the function n times. That came out to be nothing but k factorial over 2 pi iota, and the integral. Remember, z is just a dummy variable, so it doesn't really matter. I can use some psi or something. This guy. So this is a nice connection between the derivatives and contour integration. So as an application of this, now let's consider the series expansion of a complex function. So let's say I have fk, and I consider a series of the form fk0, some sort of a Taylor-like series, so on and so forth. So that's just an k minus k0 n, 0 to infinity. Okay, so an was nothing but, if I compare it with this formula over here, and I'm taking the derivative and evaluating it at a particular point. I'm taking for the nth term, I'm taking the nth derivative over here. So an is nothing but in the Taylor expansion, this guy, nth derivative at k0, which is nothing but from my Cauchy's integral formula and the analysis which I did connecting the derivatives to the integral. It is just this guy. So this is the expression of the Taylor series uh, in terms of the contour integrals. And remember, the region C will specify the region where the series converges. So, for example, rewriting this, now we did it in terms of okay, but it doesn't matter. Let's just rewrite this as fz was in terms of its Taylor series was given by this guy. So now if fz has a pole at z0, well then notice that our conditions for the derivation of the Cauchy's integral formula do not hold. And hence, we can't use that expression for the Taylor series it to evaluate Taylor's series. But in our next class we are going to see that we've already seen that a function gz expressed as z minus 0 0 to the power of p fz, where z0 was the location of the pole, and that will be analytic. If I have a, where the p is the order of the pole. So then what we can do is that we can write a Taylor series for gz, which is going to be some 0 and something like that. But let's do it in the next lecture. We'll do this in the next lecture, which is going to lead us to Taylor series and Maclaurin series and so on and so forth. I'm just going to end this lecture by another similar kind of a thing. What we have, we will just, so let's end this with another observation. So I have two contours, C and gamma, and I have a region R. So the observation is that if Fz is analytic in the region R between contours C and gamma, then I have this equality. The integral evaluated over the contour C is equals to the integral evaluated at contour gamma. So how do we show this? Well, we are going to use similar method. So what I'm going to do is that I'm going to define my new path, which is traversing this contour, and then let's say it goes here, it goes here again. So I'll call them C1, C2, and there's a gap here. And I'm again going to happily go merrily on my way. So this contour, this journey, I'm going to call as gamma. So the deal is to see this is that we shrink the gap such that C1 and C2 overlap but are opposite. So gamma equals to C plus C1 plus C2 minus my gamma. So that's essentially what my contour is. So I beg your pardon, in my contour I have to include this also. So my contour goes through this. This is my journey, and notice I'm traveling the gamma contour in the clockwise direction. So that's why I have a minus sign over here, minus sign, and then I come out of it. So this is my contour. This entire red patch is my contour. So what do I get? I get the integral fz dz is equals to integral over all these guys. Okay. So now I know that this guy is zero. Since I have this particular contour and the function was analytical in entire this region, so that is guy is zero. C1 and C2 overlap but are opposite, so they both cancel each other. That's going to be zero. So all I am left with is, and by the way, gamma was this guy minus gamma because it was in the clockwise direction, but since I have already included the minus sign, this was this. So I have shown that evaluation of the integral over contour C is evaluation of the integral over gamma. Well, I am clumsily calling this guy and this guy both as gamma, but you get the point. This is maybe the smaller gamma, you can say. So smaller gamma. So that was what was required to show. And as an aside, there's another theorem. Uh, I might not be able to spell it right. It's called Morera's theorem, which simply says that if it's the converse of it, if the integral over the contour is zero, so it involves proving that fz is analytic in the region. We've already shown this way. Yeah. So, okay, with these observations, we end this lecture. Next lecture, we are going to do residue theorems, Maclaurin series, application of residue theorems, so on and so forth. All right. Thank you.